Hello everyone. In this video, we are going to show you the details how a 70 watts audio power amplifier is designed and built. In order to make the design easier to follow, we break down the power amplifier into 6 sections. For example, input stage, voltage amplifying stage, output stage, and so on. We will discuss the functions and structures of each section one by one. Okay, let us dive into this audio power amplifier project now. This is the schematic of the 70 watts power amplifier. We will soon see how the amplifier is divided into 6 sections. This is a high-quality audio power amplifier in terms of measured and sonic performances. At 10 watts output to an 8 ohms load, the total harmonic distortion plus noise is as low as 0.02%. When a suitable power transformer is used, the power amplifier can deliver over 80 watts to 8 ohms and over 100 watts to 4 ohms. A complete PCB layout is designed, and it contains the power amplifier, DC power supply, and loudspeaker protection. You can download free PCB Gerber files in the following website. The link to the website is given in the video description below. Now, let us come back to the schematic. The blue rectangle is the input stage of the power amplifier. Here is the voltage amplifying stage, or simply called VAS. It is then followed by the output stage. After these 3 stages, the schematic is now simplified into this block diagram. A1, A2, and A3 are the voltage gains for these stages, respectively. We can now outline the 3 remaining sections from this block diagram. This is the input filter, which is located right in front of the input stage. Then we have this output filter, which is located right after the output stage. The last section is the feedback network, which samples the output signal, then feeding back to the input stage. Therefore, the entire power amplifier's voltage gain is determined by this feedback network. These sections are now named from 1 to 6. Each of these sections is discussed below. If you have not subscribed to the channel yet and are enjoying these kinds of videos, then hit the bell button and the subscriber button so that you will be notified immediately when a new video comes up next time. The input filter is the first section we now start to look at. Here are 3 input filters, or networks, commonly found in power amplifier. They are labeled as A, B, and C. Input filter A is the same one being used in this power amplifier. It operates as a low-pass filter, which is formed by resistor R1 and capacitor C1. If a signal has a fast rising and falling edge, in this example a square wave, the low-pass filter will soften the edges as shown in the picture. In a real world, it could be a fast transient signal with large amplitude getting into the power amplifier. The low-pass filter softening effect is useful as it helps minimize the chance of overloading the input stage of the power amplifier. However, just the input filter alone will not completely avoid this from happening, but the input stage also needs to reduce the voltage gain at the same time. We will come to this when we discuss the input stage. What will happen if the input stage is overloaded? If this happens, one or more transistors in the input stage are saturated so that the input stage is pushed out of the active mode. The input stage stops operating momentarily. Therefore, the result is a very distorted output. The cutoff frequency for the low-pass filter used in this power amplifier is over 200 kHz. If we want to increase the softening effect, the cutoff frequency can be lowered by changing the values of R1 and C1. However, the cutoff frequency has to be over 100 kHz so as to avoid affecting signals within the audio band. Components R1 and C1 form the low-pass filter. What is the purpose of resistor R2? As a matter of fact, R2 is an important component. Resistor R2 helps the input stage to establish DC quiescent bias properly. Imagine if R2 is not in place. What is the DC potential at the input? As no DC current flows through a capacitor, in this case C1, the DC potential at the gate of the JFET, Q1, is undetermined. If R2 is not in place, only when a line stage amplifier is connected to this power amplifier, the DC quiescent bias of transistor Q1 can be established. If R2 is not in place, the power amplifier is not stable unless a line stage amplifier is connected to it. This is not desirable. Therefore, R2 must be always in place. When R2 is in place, the DC potential at the gate of transistor Q1 is ground level. Since there is no gate current, there is no voltage drop across resistor R2. As a result, we can use a large resistor for R2, 100 kilo ohms, which is also the input impedance of this power amplifier. If JFET is now replaced by bipolar transistors, there will be a small amount of DC current flowing into the base of the transistor. There is a DC voltage drop across resistor R2. Therefore, the DC potential at the top of resistor R2 is slightly below ground level. We can only use a smaller resistor R2, which is 10 kilo ohms here. This is to avoid building up a large DC offset voltage in the input. Otherwise, it will lead to a high DC offset voltage at the power amplifier's output. Then we need to employ a DC servo to bring down the output DC offset voltage. However, the output DC offset of this power amplifier is only 0.1 volts, which is low and therefore, no DC servo is needed. This makes the power amplifier simple and easy to build. If you want to see how a DC servo is designed, write down in the comment below. We may produce a video of DC servo design in the future. Okay, let us move to the second input filter, B. This is just the opposite of the first one, which is a low-pass filter. But this input filter is a high-pass filter. As a high-pass filter, it does not soften the edges like the low-pass filter does. Capacitor C1 is placed in series with the input source, for instance, a line stage amplifier. Therefore, C1 will block any DC voltage coming from the input source. This helps reduce the output DC offset of the power amplifier. Since the capacitor is right in the signal path, good quality capacitor should be used. This is the input filter, C. As a matter of fact, it is just a resistive network rather than a filter, because it does not contain any capacitor or inductor. It is just one resistor, which is in the place so that the DC quiescent voltage can be set up properly. This arrangement is commonly found in op-amp applications. After the input filter section, we now move to the input stage. One of the functions of the input stage is to produce a voltage gain, A1. It amplifies the difference between input signal and feedback signal. The output of the input stage can be expressed in this form. The difference between input and feedback signal is multiplied by the voltage gain A1. If we look at the input stage closely, we can see that transistors Q1 to Q4 form the cascode differential amplifier. It has wider bandwidth than a conventional differential amplifier. Resistors R5 and R6 reduce transconductance, and as a result, voltage gain is reduced. However, it improves slew rate of the differential amplifier. The higher the slew rate, the power amplifier can handle large transient signal better. Transistors Q5 and Q6 establish a tail current, roughly 3 mA, for the differential amplifier. Zener diode D4 and resistor R11 establish a DC quiescent potential to the base of transistor Q3 and Q4. Because the entire power amplifier shares the same DC power supply, the ripple voltage in the power supply will be inevitably passing to the input stage. Here resistors R22, R23 and capacitors C11, C14 form RC filters so that the input stage sees a cleaner DC power supply with less ripple voltage. Even though the global feedback will eventually help reducing the noise and distortion, it is always a good practice to keep the input stage with as little noise as possible to begin with. C2 is a frequency compensation capacitor that stabilizes the amplifier at high frequency. Now, let us take a look of a conventional differential amplifier using JFET and determine the voltage gain. In a moment later, we compare it to the one with bipolar transistors. Even though the actual differential amplifier is a cascode configuration, this conventional differential amplifier will illustrate the differences between JFET and bipolar transistor for use in the input stage. When 3 mA tail current is established, each JFET has a DC bias current 1.5 mA. Given with resistors RD and RS, the voltage gain is equal to minus 24.8. This is the differential output voltage gain. For single-ended output, the gain is reduced by half. Now, we replace the JFET by bipolar transistors with the same DC bias current and resistor values. We calculate the transconductance of the amplifier. The voltage gain becomes minus 43.5, which is almost double of the JFET. If we want to keep the same voltage of the JFET differential amplifier, the emitter resistor can be increased to 71 ohms. Let us summarize what we have just found. If the DC bias condition and resistor values are kept unchanged, bipolar transistors produce much higher voltage gain. Therefore, we can afford to use a large emitter resistor RE while keeping the same voltage gain. This is why we often see that bipolar transistor input stage employs larger emitter resistors than JFET input stage. When properly designed, both JFET and bipolar transistors make good input stage. When an input stage with well-controlled voltage gain and together with the use of a low-pass input filter, the input stage will be less susceptible to be overdriven by large transient signals. Now, we move to the voltage amplifying stage. One of the functions of the voltage amplifying stage is, of course, to produce a voltage gain. As a matter of fact, the voltage gain of this stage is very high so that it contributes to a very high open-loop gain for the entire amplifier. Additionally, this stage also creates a DC voltage spread to bias the output stage. This is where the voltage amplifying stage is located. If we look at it closely, transistor Q7 operates as a buffer, which is in an emitter-follower configuration. It provides a high impedance to the input stage and a low output impedance to transistor Q8. Transistor Q8 operates in a common emitter configuration. The collector load resistor for Q8 is the collector impedance of Q10, which is a very high impedance. As a result, the amplifying stage produces a very high voltage gain. Diodes D1 to D3 and resistor VR creates a DC voltage spread so as to bias the output stage transistors. Transistors Q9 and Q10 form a current source for establishing a DC bias current for transistor Q8. Capacitor C6 stabilizes the amplifier at high frequency. The expression for the DC voltage spread is given here. Given with the estimated diode forward voltages, the DC voltage spread varies from 3 volts to 4.85 volts. A conventional method to set up the DC voltage spread is to use bipolar transistor Q20 in a so-called VB multiplier configuration. With the use of resistors RA and RB, the expression for the DC voltage spread is given in terms of RA, RB, and VB of Q20. There are 2 examples of RA to RB ratios, 4 and 6. The DC voltage spread becomes 3 volts and 4.2 volts, respectively. It is noted that diodes D1 and D2 comes from the ThermalTrak transistors Q15 and Q16, respectively. One transistor and one diode are embedded into a single 264-5 lead package. Therefore, the change of the transistor's base to emitter voltages are tracked instantaneously at all time. Here is the front page of the datasheet for transistor Q15 and Q16. The diode and bipolar transistor are physically embedded into the same package, but they appear at different locations in the schematic. Diodes D1 and D2 in the voltage amplifying stage, while transistors Q15 and Q16 in the output stage. The last thing in the voltage amplifying stage that we want to discuss before moving to the output stage is the 2 current sources that appear in this stage and the input stage. This current source has the identical configuration to the one appears in the input stage and voltage amplifying stage. Transistor QB and resistor RB are sitting on a negative power supply Vs. As negative power supply is sometimes a bit difficult to visualize, we shift up the power supply by an amount of Vs. Therefore, transistor QB and resistor RB are now sitting on the ground. Both circuits are identical in DC point of view. When both transistors in active mode, the DC potential across resistor RB is equal to the base to emitter voltage of transistor QB. In order to ensure QB operates in active mode, we set 1 to 2 milliamps DC bias current for QB. Then the constant current produced by the current source is given in this expression. It is noted that the constant current does not depend on the power supply Vs. This is the reason why it is often called as voltage-independent current source. This property is good to have because the DC power supply voltage fluctuates very often in power amplifier. Here, we have an example. We use the same resistor values from the input stage and assume the VB for both transistors is 0.6 volt. The DC bias current for QB becomes 1.3 milliamps. Finally, the constant output current is 3 milliamps. After completing the voltage amplifying stage, now we move to the output stage. The key functions of the output stage include producing very high current gain, unity voltage gain, very low output impedance, and wide bandwidth. This is where output stage is located. If we look at the output stage closely, it contains 3 pairs of emitter followers. This configuration is often called emitter follower triple. The first pair of emitter followers is called pre-driver. The second pair of emitter followers is called driver. The third pair of emitter followers is just called output emitter follower. We know emitter follower has a voltage gain close to, but less than unity. Therefore, the overall voltage gain is also close to, but less than unity. However, the emitter follower triple has a colossal current gain, which is a product of all 3 current gain multiplied together. For example, if each transistor has a current gain of 100, the overall current gain becomes 1,000,000. If the load draws a 10A current, the base current required by the pre-drive transistor is only 0.01 milliamps, or 10 microamps. On the other hand, if the load impedance is 4 ohms, the input impedance looking into the base of the pre-driver transistors becomes 4 megaohms. Because of low input current and high input impedance, the output stage does not load down the voltage amplifying stage. Here's a question. In delivering 70 watts output power to an 8 ohms load, what are the base currents I1, I2, and I3 in each of these emitter followers? To answer this, let us first determine the output current, which is 2.96 amps. Then we estimate the current gain for each transistor from datasheet. To make it simple, we assume NPN and PNP transistor has approximately same current gain. Therefore, I3 is equal to 2.96 milliamps. This is the base current of Q15, and it is also the emitter current of Q13. I2 is equal to 0.19 milliamps. This is the base current of Q13, and it is also the emitter current of Q11. I1 is equal to 1.9 microamps. In this power amplifier, we set the DC bias current on the emitter follower triple as shown in the diagram. The DC bias currents are well above the required DC bias current at 70 watts output. The output transistors are biased at 140 milliamps so that the power amplifier is running at class AB. This is also called the idle current, as this is the current running at the output transistors even at no load condition. Since the driver and output transistors are running quite warm, they have to be mounted on heat sinks. This picture shows the heat sinks used for the driver and output transistors. Diodes D1 and D2, transistors Q15 and Q16 are mounted on the same heatsink. As you have just seen, the power amplifier is biased in class AB. However, you may want to ask, is class AB the only choice available? What would happen to the amplifier if we set the output transistor's DC bias current to 0? As a matter of fact, we can set the output transistors at no DC bias current. The output transistors and the power amplifier become operating in class B, in which the output transistors are in the cutoff mode when there is no input signal. It is useful for public address system as the efficiency for class B amplifier is high. However, class B amplifier produces high distortion. It is not a desirable for use in hi-fi. Let us take a look how the output transistors operate in Class B. First of all, there is no DC bias current. There is a sinusoidal input signal, and the output stage is connected to a load. Transistor Q15 is turned on by the positive input signal, while Q16 remains in the cutoff mode. Since in the beginning, transistor Q15 is in the cutoff mode, it does not amplify anything until the input signal exceeds the base emitter voltage, which is around 0.6 volt to 0.7 volts, before Q15 is turned on. Therefore, there is a loss of signal in the transition when the transistor is switched from cutoff to turn-on mode. Transistor Q16 is turned on by the negative input signal, while Q15 remains in cutoff mode. With the same token, in the beginning the transistor Q16 is in the cutoff mode. It does not amplify anything until the input signal exceeds the base emitter voltage. Again, there is a loss of signal in the transition when the transistor is switched from cutoff to turn-on mode. When we combine the positive and negative cycle of the output waveform, there is a notch appeared in the middle. As a result, this produces the so-called crossover distortion. Since the crossover distortion is caused by the output transistors in cutoff mode, the distortion cannot be reduced by applying global feedback. No matter how much amount of feedback is applied, crossover distortion remains the same. The input-output characteristic of the Class B output stage can be expressed in this graph. It is clear that in the positive and negative cycle, when the amplitude of the input signal is less than the base to emitter voltage of the transistor, no output signal is produced. On the other hand, when the output transistors are operated in Class AB, in which there is a small amount of DC bias current running in the output transistors, they are operating in active mode. The input-output characteristic curve within the two VBE voltages has a different slope that produces a slightly high distortion. However, when global feedback is applied, the distortion will be greatly reduced to a very low level. On the other hand, there is a Class A power amplifier, in which the output transistors are operating in a high DC bias current, so that the transistors are always turned on. If you are interested in Class A power amplifier design, write down in the comments section below. We may produce a video about how to design Class A power amplifier in the future. Now, let us move to the output filter section. The output filter is often called Zobel network. Resistor R21 and capacitor C8 forms a low-pass filter that helps stabilizing the amplifier at high frequency. Inductor L1 produces an impedance to stabilize the amplifier when driving capacitive load at high frequency. A small resistor, for example 1 to 2 ohms, can be also used to connect in parallel with the inductor L1, so as to release the energy being stored in L1. This is especially useful for very high output power amplifier. After completing the output filter, we now move to the feedback network. One of the key functions of the feedback network is to establish the voltage gain for the power amplifier. This is achieved by sampling the output and feeding to the input stage. Once the feedback is applied, it brings several benefits to the amplifier. Distortion and output impedance are reduced, while bandwidth is broadened. Capacitor C3 stabilizes the amplifier at high frequency. Capacitor C4 sets the amplifier to unity gain at DC. I have found two feedback values I like for this power amplifier. One is to pick 510 ohms for resistor R10. It produces voltage gain 24.5. The other one is to pick 560 ohms for resistor R10. It produces voltage gain 22.4. This gives slightly higher feedback to the amplifier than the case of 510 ohm. If you have the chance to build this amplifier, try these two feedback values and let me know which one you like better. Capacitor C4 is also an important component. It does not affect the gain of the amplifier from mid to high frequencies. However, at DC ground level, the gain becomes unity. Therefore, it helps keeping the output DC offset low even no DC servo circuit is used. The output DC offset for this power amplifier is 0.1 volts, which is good enough. Choose a large capacitor C4 so that the cutoff frequency is far below the audio band. As you can see here, no DC servo circuit is employed in this power amplifier. However, if you are interested in knowing how a DC servo circuit is designed and used, write it down in the comment below. If there is sufficient number of people interested in it, I will produce a video on that topic. Here is the power amplifier based upon the schematic and PCB discussed in this video. Each channel has a separate power transformer. The power amplifier produces more than 70 watts to each channel. The sound is remarkable. Let us take a look of the power amplifier's measured performances. The sinusoidal and square wave responses at different frequencies are clean, without any unwanted oscillations and anomalies. Here is to test the stability of the power amplifier. A 10 kHz square wave signal is fed to the amplifier with an 8 ohms resistive load, and a 1 microfarad capacitor is connected in parallel to the 8 ohms load. As seen in the picture, a small and well-controlled oscillation appear on the positive and negative cycle of the square wave. The waveform is clean without any sign of uncontrolled wild oscillation. For 8 ohms load, bandwidth of the power amplifier at 70 watts output power is 60 kHz. At 10 watts output power, the bandwidth is over 100 kHz. At 10 watts output power to an 8 ohms load, the distortion plus noise is 0.02%. Same output power to a 4 ohms load, distortion plus noise is 0.03%. For 8 ohms load, the output power can go up to 80 watts before the amplifier starts to clip. For 4 ohms load, the output power can go over 100 watts. However, when the amplifier will start to clip is really depending on the power capacity of the power transformer. For the power amplifier I built, I used two 150 VA power transformers. A 2-channel 70 watts power amplifier requires 2 PCB. Each PCB contains 3 parts. It contains DC power supply, loudspeaker protection circuit, and the power amplifier circuit. Therefore, this is just one single PCB that you need to build a complete channel of a 70 watts power amplifier. You can download free PCB Gerber files in the following website. The link to the website is given in the video description below. If you have not subscribed to the channel yet and are enjoying these kinds of videos, then please think about clicking the subscriber button below so I can continue to make these videos for you. I will see you in the next one.